In this video, we are going to discuss alternating series and conditional convergence. Alternating series test. Most of the tests we saw so far only dealt with the series with the positive terms, but now we're going to discuss this test which talks about alternating series, the series where terms switch from positive to negative, negative to positive. An alternating series cannot have two terms of the same sign back to back. So it can be positive, negative, positive, negative, or it can start with negative, negative, positive, negative, positive. So signs will be switching. Alternating series test states let an be greater than 0. The alternating series summation n equals 1 to infinity negative 1 to the power n an and summation n is equal to 1 to infinity negative 1 to the power n plus 1 an will converge if these two conditions are met. The first condition is the limit n goes to infinity an is equal to 0. The second condition is an has to be decreasing. If these two conditions are met, then we can say the series converges. If these two conditions fail, then the series diverges by nth term divergence test. So let's see some examples of using the alternating series test. Determine the convergence or divergence of the following series. So we have an is 1 over n. We see limit n goes to infinity an, limit n goes to infinity 1 over n is equal to 0. So the first condition is met. The second condition was that an is decreasing, which we can see it is a decreasing series. An plus 1 is smaller than an because my terms here would be 1, 1/2, 1/3, 1/4, and so on. Terms are getting smaller and smaller. So if these two conditions are met using alternating series test, the series n is equal to 1 to infinity negative 1 to the power n plus 1, 1 over n. This series converges using alternating series test. This series converges. Let's see another example. This series is not written like an alternating series, so we're going to have to first write it in the alternating series form. So let's go ahead and write the first few terms. When n is 1, my first term would be 1 over negative 2 to the 0 power. When n is 2, I would have 2 over negative 2 to the 2 minus. When n is 1, 1 minus 1 is 0. When n is 2, 2 minus 1 is 1. When n is 3, I would have 3 over negative 2 to the power 3 minus 1 is 2. N is 4, that would be negative 2 to the power 3, and so on. So these are just first few terms I wrote to see how can I express it in terms of alternating series, if it's possible. So my first terms are to be 1. Next term is negative... Next term is negative 2 over 2, which is negative 1. Negative 2 over 2 is 2 over negative 2 is negative 1. 3 over 4, it's going to be positive 3 over 4. And then, let's see it again. It doesn't look like it's going to be alternating series. Let me rewrite the terms, and I'm going to give myself more room. I have to squeeze in smaller space, so I'm looking at part B. Let's write the first few terms. The first few terms, when n is 1, 1 over negative 2 to the power 1 minus 1 is 0. When n is 2, 2 over negative 2 to the power 2 minus 1 is 1. When n is 3, 3 over negative 2 to the power 3 minus 1 is 2. 4 over negative 2 to the power 3. 4 minus 1 is 3, and so on. So my first term is 1. Second term is 2 divided by negative 2, which is negative 1. The third term is 3 over 4. The fourth term is negative 4 over 8. So we can express it slightly differently. We can pull out the negative 1 to express this series as n is equal to 1 to infinity. My first term is positive, second term is negative, third is positive. So I'm going to say n plus 1 and n over 2 raised to the power n plus n minus 1. So we just rewrote the series. We pulled out the negative 1 from here. And if I use the exponent n plus 1, when n is 1, my first term will be positive. When n is 2, my second term will be negative. When n is 3, my third term will be positive, and so on. So I was able to rewrite this series in a slightly different form to make it alternating series. Now let's use the alternating series test. So conditions for alternating series is the an here, an is n over 2 raised to the power negative 1. So first condition was the limit n goes to infinity, n over 2 to the power negative 1 is equal to, this limit is going to go to 0. Because in the denominator we have exponential function, in the numerator I have like y equals x. So think about it, you have y is equal to x in the numerator, 2 to the power x minus 1 in the denominator. Exponential function in the denominator and linear function in the numerator. Linear function does not grow as fast as the exponential function, so denominator is growing much faster. This limit is going to go to 0. Second condition was that it has to be a decreasing series, which one we have the negative 1 and then 3/4 and negative 4/8. So an plus 1 is less than an. The next terms are getting smaller and smaller. It's a decreasing series. Thus, using alternating series test, we can say the summation n is equal to 1 to infinity negative 2 to the power n minus 1 converges. This series converges. See another example, number 3, alternating harmonic series. We earlier saw that harmonic series in itself is divergent series. Harmonic series is diverging. Let's look at alternating harmonic series. Alternating harmonic series, that would switch, the signs of the terms would be switching here. An is equal to 1 over n. An is 1 over n here. So the first condition is limit n goes to infinity of an. So that's going to be limit n goes to infinity of 1 over n. This is going to go to 0. So first condition is met. The second condition was an plus 1 is less than an, which is also true in this case. An is decreasing. The next terms are getting smaller and smaller, because if I plug n as 1, my first term would be 1, second is 1/2, third is 1/4, 4 is 1. Although I'm switching sign in the first one, I'm going to have a negative, positive, and so on. But my terms of an are decreasing. So when I think about an, I'm only talking about this piece. An is decreasing. It's a decreasing series. So using AST, we can say, using alternating series test, summation n is equal to 1 to infinity, negative 1 to the power n, 1 over n. Alternating harmonic series converges. Alternating harmonic series converges. Now, we saw earlier that harmonic series in itself diverges. Summation n is equal to 1 to infinity is divergent. And we can easily prove this. The harmonic series is divergent, but alternating harmonic series is convergent. We just saw that. We can prove that harmonic series is divergent using the integral test. So 1 to infinity 1 over x dx, which we can say limit r goes to infinity 1 to r 1 over x dx. So that's going to be natural log of x 1 to r, and r goes to infinity. So natural log of infinity, or natural log of r minus natural log of 1. And we know natural log of r goes to infinity when r goes to infinity, x goes to infinity, natural log of x goes to infinity. So this is going to be divergent. Alternating harmonic series in itself is divergent, but alternating harmonic series is convergent. That means we can find the sum of alternating harmonic series is finite, but sum of harmonic series is infinite. We cannot find the sum. Absolute and conditional convergence. Absolute convergence, if a series summation absolute value of a of n converges, then the series summation a of n also converges. So if the absolute value of a of n converges, then the series also converges. The converse is not true. For example, alternating harmonic series. We just saw that alternating harmonic series converges, but alternating harmonic series in itself does not converge. That one is divergent. This type of convergence is called conditional convergence. If an be absolutely convergent, if absolute value of an converges, an is conditionally convergent if absolute value of an diverges. So let's check out a couple of examples of conditional convergence and absolute convergence and conditional convergence for alternating series. So for part A, we are given a series negative 1 to the nth power n factorial over 2 to the 2 raised to the power n. And we are looking for absolute or conditional convergence. Okay. We could also use the ratio or root test here, and we can use the alternating series test as well. In this video, my focus is alternating series test. So an is to be back to the pen. An in this case is n factorial over 2 to the power n. An is the piece that's attached to negative 1 to the nth power. Let's see. So first condition is limit n goes to infinity, n factorial over 2 to the power n. Where does this limit go? Well, this limit, on the numerator, I have factorial function. In the denominator, I have 2 to the power n. Let's just go ahead and think about n factorial is 1 times 2 times 3 times 4 times 5 times 6 and so on, 3, 4, 5, 6, 7, 8, 9 and so on. And 2 to the power n is 2 times 2 times 2 times 2 times 2 times 2 times 2. So you can clearly see that your denominator does not grow that fast. The numerator is growing much, much faster. Factorial function grows much faster than the exponential function. So this limit is going to go to infinity. Okay, so if this limit goes to infinity, then we don't even need to check the second condition by nth term divergence test. Nth term divergence test. By nth term divergence test, the series diverges. This series diverges, the one we had in the question, negative 1 to the power n, n factorial over 2 to the power n diverges. Let's check out another example, part B. Here again, we are looking for conditional and absolute convergence. The first one diverges, so no conditional convergence, no absolute convergence. The second one, we have negative 1 to the power n square root of n. Here, an is 1 over square root of n. So limit n goes to infinity, limit n goes to infinity of a of n, limit n goes to infinity a of n is limit n goes to infinity 1 over n. When n goes to infinity, 1 over n is going to go to 0. So the first condition is met. The second condition is that 1 over square root of n is decreasing. We can write the first few terms and see that. We can see that the n plus 1th term will be smaller than the nth term because we have 1 over square root of 2, 1 over square root of 3, 1 over square root of 4, 1 over square root of 5, and so on. So my terms are getting smaller and smaller as I'm going further in the series. So this is decreasing. If that's the case, then let's also check. So using AST, we have conditional convergence. Using AST, we have conditional convergence. Using AST, we have conditional convergence. Now let's go ahead and check for absolute convergence. Let's also check for absolute convergence. Check for absolute convergence. For the absolute convergence, we said that the absolute value of an should also, absolute value of an would be 1 over n to the power 1/2 square root, absolute value of 1 over n to the power 1/2. This is a divergent p-series. This is a divergent p-series because your p-value is 1/2. P is equal to 1/2, which is less than 1. If your p lies between 0 and 1, then the series diverges. So in this case, no absolute convergence, but we do have conditional convergence. No absolute convergence, but we do have conditional convergence. Yes, we have conditional convergence here. No absolute convergence. Okay, next example, part C. If you check for absolute convergence, then if you check for absolute convergence and you get a yes, then that means you also have conditional convergence. So here, my series is, my an is 1 over n plus 2. An is 1 over n plus 2. Let's check for conditional convergence really quick. Conditional convergence has two conditions. The first one is limit n goes to infinity, 1 over n plus 2 is going to be 0. So first condition is met. The second condition is an plus 1 is less than an. That means it's a decreasing series, which is also a yes, because we have 1 over, if I plug n as 1, 1 over 3 is my first term, 1 over 4 is second, 1 over 5 is second, 1 over 6. So it keeps on going as starting with 1/3 and the terms are getting smaller and smaller. So we can say, yes, we have conditional convergence. Conditional convergence. We do have the series converges conditionally. We do have conditional convergence. Let's check for absolute convergence. Let's check for absolute convergence now. So I'm going to look for absolute convergence now. For absolute convergence, we need to go ahead and find out the absolute value of 1 over n plus 2. So let's see if summation n is equal to 1 to infinity 1 over n plus 2 absolute value converges or not. So we can use the integral test in this case, or we can also use comparison test. I'm going to go ahead and use the integral test. 1 to infinity 1 over x plus 2 dx. That's going to be natural log of x plus 2 going from 1 to infinity. And I shouldn't be plugging the bound in infinity. I should be using r and saying r goes to infinity. But I can quickly see here, it's going to be natural log of infinity minus natural log of 3. Natural log of infinity, this goes to infinity when x goes to infinity, natural log of x also goes to infinity. So this is going to be divergent. In this case, this is going to be divergent. Again, we don't have any absolute convergence, but we do have no absolute convergence, but we do have conditional convergence. No absolute convergence, but we do have conditional convergence in this case. See one more example. Negative 1 to the power n plus 1 over n cube root of n. Okay, so I'm going to rewrite the series. Negative 1 to the power n plus 1 times 1 over n to the power 1/3 plus 1. And is equal to 1 to infinity. Negative 1 to the power n plus 1, 1 over n to the power 4 over 3. Okay, so that's the series I'm looking at. So let's first think about conditional convergence. Do I have conditional convergence for this series? Conditional convergence. Conditional convergence has two conditions. The first condition is the limit n goes to infinity, a of n should be equal to 0. Let's see if that's the case. When n goes to infinity, 1 over n raised to the power 4 over 3, that does go to 0. So the first condition is met. The second condition is an is decreasing series. Let's see if that condition is met as well. When I plug n as 1, my first term is 1. My second term is going to be 1 over 2 to the power 4 over 3. 1 over 3 to the power 4 over 3. 1 over 4 to the power 4 over 3, and so on. So yes, that condition is also met. It's a decreasing series. Both the conditions are met. So using alternating series test, using AST, series converges conditionally. We do have conditional convergence. N is equal to 1 to infinity. Negative 1 to the power n plus 1 over n cube root of n converges conditionally. Now let's check if we have absolute convergence or not. So let's check for absolute convergence. For absolute convergence, the absolute value of a of n should converge. Check for absolute convergence. Check for absolute convergence. So an should converge for absolute convergence. Summation n is equal to 1 to infinity. An must converge for us to have absolute convergence. Now let's see if that's the case in here. So summation n is equal to 1 to infinity, absolute value of an, which is 1 over n to the power 4 over 3. This series, we do know it's a convergent p series, as this is a convergent p series because your p value is 4 over 3, which is greater than 1. Thus, we do have absolute convergence in this case. We do have absolute convergence, and if you have absolute convergence, that means you definitely have conditional convergence. You didn't have to check for conditional convergence if you would have checked for absolute convergence first. Absolute convergence, yes. So in this case, we do have absolute convergence. So we talked about the alternating series test in this case.